Okay, here I'm going to examine the relationship between empirical probability and theoretical probability. To do it, I'm going to perform an experiment involving flipping coins. I've got a coin here, um, which I can flip in reality, but you could also do it virtually using the website random.org, and then we'll put /coins. Let me go ahead and bring up that site just for a second here. And I'll show you what it looks like. Okay, yeah, so here, as it says, the site samples atmospheric noise for effectively random data. And it's going to apply that to the idea of flipping a coin. And we can decide how many coins we want to flip. I'm just going to do one for right now. And let's flip that coin. Okay, it came up tails. So now I'm going to go back to my chart here. And all I want to do is fill in the result that I had gotten. So I'll put a tally mark here by tails and no tally mark for heads. And I'm going to calculate an empirical probability from the results that I just got. Now, a success is defined as getting heads, but we got tails. So I'm going to put zero successes out of one flip. And let's get the decimal version of that. It's going to be just a zero. Okay, now I want to flip the coin again, but this is a cumulative empirical probability, meaning we want to keep track of what happened in the past and build on that. So I'm going to bring down the tails result that I got. Now I just need to actually flip the coin one more time. So I'll do that here. It came up tails again. So now when I go to calculate my cumulative empirical probability, there were zero successes out of two flips, and I still have a probability of zero. I'll bring my results down just like before, and now I need to only flip the coin one more time. All right, this time it came up heads. So my cumulative empirical probability now becomes 1 out of 3. And we want to get the decimal form of that, which is approximately 0.333. Okay, bring the results down, and then let's just flip it one more time. Okay, it's heads. So that takes us to a cumulative empirical probability of 2.4, which is 0.5. Now I didn't want to make a row for every flip. So my next is going to be 8. What I'm going to do is I'm going to bring down the results of the past, but I need 8 total flips. So I've got to flip the thing 4 more times. Okay. Okay. This time my probability is 5 out of 8, 0.625. Okay, we'll bring those results down. Let's flip the thing 8 more times. Okay. 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 Looks like I've got 7. Oops. Too many there. 7 out of 16. And calculator, that is 0.4375. Okay, great. So the next thing I'm going to do here is I'm going to bring those results down. And I need to flip the thing 16 more times. Now I'm going to do that on the website here. There's so many flips. Okay, the website gives me these results. Okay, so I actually got 17 out of 32. 0.53125. All right, great. Now that we're done with that, let's go ahead and plot the results that we found on the graph. So I'm going to start with the first toss. After the first toss, I had a cumulative empirical probability of 0. Then after the second toss, it was still 0. 0 is at the bottom, of course. 1 would be at the top. Then after 3 tosses, my empirical probability went up. And after 4 tosses, we went up even higher to 0.5. Then after 8 tosses, I was at 0.25. After 16 tosses, I had 0.4375, so I dropped back down. And then finally, 0.53 for 32 tosses. Now, we want to see the trend over time. And not just that, but let's also plot what we know the theoretical probability to be. So we already, in the past, have calculated a theoretical probability for the coin toss. It is found by the tree, and there is 1 success in the tree out of 2 possible outcomes. So the true theoretical probability is 0.5. Now let's go ahead and make a nice horizontal line where that occurs. That's a really important value. Okay, cool. Now, when it comes to the empirical probability, cumulative empirical probability, I just want to kind of connect the dots as best I can into a smooth graph to see what's happening over time. And so what appears to be happening is that when we first started the experiment, we couldn't get the theoretical probability of 0.5, literally, because it's one toss. So you're either going to have a probability of 0 or a probability of 1. Then at some point, we were able to match the uh, cumulative empirical probability to the theoretical probability. But it didn't stay there forever. It wavered quite a bit. But as the number of tosses increases, what we see is a trend here that the cumulative empirical probability is approaching the theoretical probability statistically over time. And so that's a very fundamental property of the universe, basically. It has a lot of applications in statistical mechanics, thermodynamics. It was a big discovery back in the 1900s that the whole reason why heat flows from hot to cold is because particles tended to lose their energy over time. And they did it for statistical reasons that are based on this type of interaction between the empirical probability and the theoretical probability. So when we say that the theoretical probability of heads is 1/2, it's like, what does that really mean when it comes to in practice in the real world? Well, it means that over the long run, over the long term, on average, 1 in every 2 tosses of a coin will result in heads. But you only really get that empirical probability for certain if you let the number of experiments head toward infinity. If you perform an infinite number of experiments, then you'll get exactly half heads and half tails. But we can't actually perform an infinite number of experiments.